So GNSS augmentation, it's used to enhance reliability, availability, and accuracy or precision, or both, of the GPS or any other GNSS system based on external information. So the GPS errors, which might be the same in the other systems since they rely on the same physical concepts and mathematical methods, they come from the ephemeris errors, which are global, the atmosphere, especially troposphere and ionosphere errors, which can be measured, and multipath errors, which may be varying a lot. So augmentation methods consist in gathering data about errors, so the clock drift, the ephemeris error, ionospheric delay, and so on. Use measurements about past errors to be able to provide fixes for the next frames. You also can rely on additional vehicle information for more complex systems. So there are several augmentation systems and several types of augmentation systems. So first we started with ground-based augmentation systems, which is called the differential GPS. And then we moved the corrections from the DGPS to space through to provide satellite-based augmentation systems such as WAAS in the USA, EGNOS in Europe, MSES in Japan, and other ones. So we see here the footprints of the systems. The receivers must be adapted to be able to receive and extract and process the information from these augmentation systems. And so let's start with why the need to use GPS augmentation systems. So remember, up until year 2K, the GPS was providing its system to everyone with the selective availability. So why the selective availability and how? So the selective availability removed some of the time information from the frames for the civilian use. So it was less precise for the propagation time, therefore less precise for the overall system accuracy. Because since the GPS was available for everyone, foreign military, so I say foreign from the USA point of view, may use the GPS too, and the Department of Defense feared that other armies in the world might use GPS to guide weapons against the US military forces or against allied militaries or assets. So the selective availability was deemed as a proper solution to provide an inaccurate enough system for civilian use while still not providing the full capability of the system to everyone. I think, but it's only my opinion, that adding something around 30 meters to the positioning error of the system is ridiculous when taking the account of the fear of the Department of Defense, since most of the guided weapons today have an area of effect of explosion which is far more than 30 meters. So if you, for instance, if you launch a tactical intercontinental ballistic missile with nuclear warheads, I don't think you really care about 30 meters error when you level down hundreds of square kilometers in the target area. So it's my opinion, but since the GPS is managed by the DoD, they do what they want to do with it. So to cope with this selective availability, which provides a high error when you are dealing with precise applications such as routing, finding a waypoint, a point of interest, and so on. And other systems are very expensive. Some administrations, even in the USA, would have liked to replace every other systems which are expensive by the GPS, which is not expensive. If the more you use it, the less expensive it is if you relate it to only one device. So the first administration was the FAA, the Federal Aviation Administration, which requested to the DoD to disable the selective availability so that planes could rely on the GPS to avoid using other expensive local systems. But this request was rejected by the DoD. So that's why the FAA they thought about this and had the idea to cope with the selective availability with an additional data that would fix and correct the errors from the selective availability. So the selective availability signal was not changed frequently, so the positioning error was quite stable, and its error was uniform on wide areas. So the idea behind the DGPS is to transmit the error to the GPS users which are in the vicinity of the DGPS station, to transmit the error correction along with ionosphere error correction, which further improve the accuracy, and to achieve a final accuracy of 10 meters, which is far better than 33 meters. So in 1996 there were DGPS stations in harbors, so limited use, and then most of the populated areas were equipped. So they started with harbors because the accuracy is less critical than airports, but airports still are very interested by one system to replace everything and to expense less money, to have less expenses in the function of the airport. So the principles are to gather information from fixed stations whose coordinates are precisely known, and by differences between the several stations you can fix the errors and inject this correction in the GPS chip, which is DGPS compatible, to improve the output location. So the errors that can be corrected are clock derivation, because first, of course, the scrambling of the clock digits mainly affects the clock derivation. The ephemeris, since the ground updates are not perfect and they are not permanent, so every 2 hours you have one update, so after 1 hour and 59 minutes you have the lowest precision in the ephemeris. It also fixes relativist effects, ionospheric error because they are local to the GPS station, and tropospheric error. So the observations are on 1, 2 or 3 satellites, and simple difference is an example here. You have your distance computed, which will depend from the distance from both satellites and the DGPS station. The difference in the clock derivation, difference is the ionospheric error, tropospheric error, ephemeris error, relativity error, and the remaining part of the errors which cannot be fixed. So the consequences of the deployment of the DGPS, which is a ground-based augmentation system, GBAS, was to improve the GPS at the cost of the station's deployment and operations and maintenance. Therefore, it was not deployed in rural environment because there are not enough people to justify expensing money for DGPS stations. However, since it rendered selective availability useless, selective availability was discarded in year 2000, and now we have the standard positioning service of the GPS to use, still fixed and improved by augmentation system. And to improve coverage of the augmentation system, the fixed information are now distributed by satellites, which makes satellite-based augmentation systems such as WAAS, EGNOS, and MSLS. So, while the DGPS was developed as a ground-based augmentation system, it has evolved to a satellite-based augmentation system, which is more global, less precise, but it provides a good accuracy to everyone within the coverage of the satellite-based augmentation system. So let's go back to why the need to enhance the GPS. So it's the Federal Aviation Administration and all over the world the aviation administrations are interested. They find, especially they find the ILS too expensive. So the ILS is the system giving your altitude when you are nearby the airport, and it makes it possible to land the plane without seeing the takeoff and landing runway, because big planes they have to point the nose of the plane upwards when they are landing, since they have their wheels are two at the rear of the plane and one on the front, so you have to put down first the two backward wheels and then only the front wheel. So you have to incline the plane nose up, so you cannot see the runway from the cockpit. So without a global positioning system which is precise enough, especially in altitude, you have to rely on the ILS, which is expensive because first the station is expensive, and second you have to have one station for each airport. So the idea to use a GPS for everything is mainly to spare some money on exploitation. and monitoring and correcting some of the errors, so mainly the ionospheric error, is possible to improve the GPS accuracy. So first was satellite based augmentation system is WAAS, the Wide Area Augmentation System. It improves the GPS accuracy, integrity and availability, which is very critical for airport. Its main purpose would be that aircraft rely on WAAS for all phases of the flight, including precision approach, which means that ideally the aircraft would be able to take off and land with its autopilot based on GPS information only. So for that it is required that WAAS is certified safety of life category 3. Today it's only category 1, but it's already providing a lot of good services to the aviation. So the WAAS current segment is 38 wide area reference stations which collect information on the GPS signals within the footprint of the system. 3 wide area master stations which generate 2 corrections, a slow and a fast, which is applied often. 2 pairs of ground uplink stations which transmit the corrections to the WAAS space segment. The space segment is composed of 2 commercial satellites, 1 PanamSat of type Galaxy 15 and 1 Telesat of ANIC F1R type, which are in geostationary orbit, which means then they are not moving related to the Earth. And they broadcast the WAAS and the regular GPS messages to further improve the system. So this is the footprint, so it covers North America, which is the target of the system. Although it covers a part of South America, its corrections cannot be used there because the corrections are only gathered here in the target footprint by the monitoring station. In the user segment, the GPS and WAAS receivers can read and use both signals and use the corrections to inside the GPS calculation, the fast correction, and then the slow correction is applied to provide the final location returned by the device. So the WAAS stations are in USA and Hawaii. The master stations will queue the messages from the reference stations and send these to the geostationary WAAS satellites every 5 seconds. And the WAAS satellites will broadcast these corrections messages to Earth to any WAAS capable receiver that can use it. Its objective is to provide an accuracy that 95% of the time will be within 7.6 meters accuracy or better, all dimensions included, and integrity, making able to detect misleading data within 6.2 seconds, and to meet accuracy and integrity requirements with no more unavailability than 5 minutes with WAAS each year, compared to the 4 hours else with only the basic GPS system. So the benefits of WAAS is to address all of the navigation problem with a highly accurate position, a low cost, only GPS receivers, so that any airport can have precision approach, since some airports which do not have big planes do not have ILS, to work between the airports and to be less expensive compared to the ILS. Its limits are to rely on geostationary orbits, which means that above 71.4 latitude you cannot rely on the WAAS signal because it's hard to get the signal from the airplanes. WAAS receivers for aircraft are a bit expensive, so $10,000 for each plane, and for now it cannot provide category 2 and 3 precision approach, so it cannot do everything, so you still have to rely on external systems. In the future it would well, maybe hopefully it will improve to aviation operations above category 1, so down to 200 feet. With software improvements in signal processing, maybe the Alaska will be covered. And the last improvement which is programmed is to add a satellite to the space segment and use the L5 frequency to further improve the corrections. So in Europe we have our own version of the WAAS system, European Geostationary Navigation Overlay Service, EGNOS. It's based on 40 ground stations. It is GLONASS and GPS compliant, and it will work with Galileo. It relies on 3 geostationary satellites under European Union and European Space Agency fundings, and it was launched in 2005. So here are some of the monitoring stations. It's the footprint of the system. So again, its real footprint is here, so you cannot use it outside because the monitoring data is not fitted to other areas. So the space segment relies on 2 satellites of the Inmarsat organization and 1 satellite from the ESA. And the GPS receiver with compatibility are SURF3 and everything later, so any current phone, for instance, can look and use the EGNOS signals. It's available since July 2005 with an accuracy of 2 meters and an availability above 99%. As a demonstration, it was used to track the Tour de France cyclists in 2005, and it was intended to be certified for safety of life in 2010, and I think it's been done since then. Another way to improve the GPS and other GNSS is to combine GNSS and Internet to improve the time required for a cold start by downloading the almanac data of the GNSS constellation, not through the GNSS signals but through the Internet, which is far faster than the 5 bits per second of the satellites. So here are some results with the SysNet signals and how quickly it can get a GPS fix, and SysNet also provides some of the DGPS fixes, so it also improves the overall error.